I'm Sean Rager, and this is my Lab 3 for Georgia Tech Physics 2, Magnetic Field of a Bar Magnet. This lab starts with our problem statement. Our goal is to find the dipole moment of a bar magnet through basic measurements of distance and magnetic fields from a magnetometer. We started by locating the magnetometer chip on the smartphone by looking for the maximum readings on axis in both the x and y directions of the phone. We then aligned the smartphone with magnetic north by rotating it until the x component was zeroed out in our readings. Next, we recorded the distances at which on-axis readings of 20, 70, 120, 170, and 220 microteslas in the x direction occurred. This would help us later form a relationship between distance and magnetic field. In the next part of the procedure, we found a distance at which the net magnetic field was 100 microteslas, and then moved the phone vertically the same distance to create a 45-degree angle. We then recorded all components of magnetic field at this location. For our observations after the experimental procedure, we found that when the magnetometer is far away from the magnet, it measures a zero magnetic field in the x direction, and the reverse is true. When the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here is our data collection. We can see all three trials at each distance, as well as all three components of magnetic field at the 45-degree angle distance. Next up are the physics principles, starting with the Biot-Savart equation at that top row, which inputs the magnetic moment as well as the radius of observation and calculates the magnetic field. Then we have the simplified on-axis approximation, which no longer needs the dot product and is notable for having a simpler formula to calculate. Both of these formulas, we can see magnetic field decreases rapidly as distance increases, as r is in the denominator and is to the third power. And the final equation at the bottom, the b bar equals kr to the power n, is our distance-dependent formula, and we will calculate k and n later using our experimental data. Here are our calculations. We plotted the distance and magnetic field measured on a logarithmic scale, and we can see according to that logarithmic equation at the top that n is equal to the slope of the graph, negative 1.2, and k is equal to e to the power of the y-intercept, or 5.65 times 10 to the negative 6th. Now n is far from the expected value of negative 3, so to calculate our magnetic moment, we will set it to negative 3. This will result in some perpetuated error, as k is not properly adjusted, and we will see this later. But for now, our calculated magnetic moment is 28.274. We use this in our glow script code, which we'll see on the next screen. We can see starting with our function dipole d, which takes in the magnetic moment that we calculated, as well as r, and outputs the magnetic field as a vector at that location. We can then see that this magnetic field was used as the axis for 7 different arrows, 4 perpendicular to the magnet, 2 on axis to the magnet, and 1 at a 45-degree magnet, just as our experimental procedure recorded, so that we can compare experimental and calculated values. We'll see the model as well as the calculated value on the next screen. Here's the model. We can see the blue arrows represent the perpendicular magnetic fields, the orange arrows represent the on-axis magnetic fields, and that red arrow in the top right corner is at a 45-degree angle, and the calculated value using our calculated magnetic moment turns out to have a net magnitude of 1.49 times 10 to the negative 4th. Now we can see that this value is much different than our recorded value for the magnetic field on the magnetometer. It's off by an order of magnitude, which is quite significant. We can review potential sources of error, which are my phone not being in quite the best shape could have thrown off the calculations. The screen is cracked. The magnet lacks radial symmetry, so if not all recordings were done at the correct orientation, that could have thrown it off. And the app may have been unreliable, maybe just exiting the app didn't properly calibrate it. Regardless, we can see that the magnetic moment that we calculated does not quite compute accurate magnetic models in GlowScript, but the physics principles we applied still show correct relationships between distance and magnetic field. Finally, with our conclusion questions, if the x component of the magnetic field was not zeroed out at the start, then we would not have been able to separate the Earth's magnetic field from the magnetic field of our bar magnet, and we wouldn't have been able to derive a proper relationship between distance and magnetic field. And if we stuck 2 identical magnets together end to end, we would see that as the magnetic force increases, as would our measurements of magnetic field, but they would not necessarily double. So those are the conclusions of how we can use measurements of distance and magnetic field to calculate the magnetic moment of a bar magnet. Thank you for watching.